If you've ever tried inquiry-based lessons and inquiry-based learning in your classroom and you didn't find success with it, whether you're teaching chemistry like me or some other secondary science, one of the reasons it might have not been as successful as you'd hoped is because the sequence wasn't optimized for not just students uncovering, digging for, through discovery, core ideas in a single lesson, but perhaps the entire unit, the entire sequence of lessons, or for that matter, the year-long sequence of units kind of spoiled it. So that's what I'm talking about in this video today. In this video, I'm going to share with you my lesson on the periodic law in high school chemistry. Now, if you teach high school chemistry, you know that usually that's taught at the forefront, the beginning of a unit on the periodic table trends, but here I'm putting it at the end. And I'm putting it at the end because it's also something, this core idea can be uncovered once students know how to do all the other things that those atoms have in common in their groups and periods on the periodic table. Hi, I'm Lisa, and I design lessons so that students practice lab skills every day without stepping foot in a wet lab, without having to buy dollar store doodads. Every day, students using the skills of observation, citing evidence, asking questions, making inferences, communicating to one another, doing all the science things, while they are themselves, in a very student-centered way, uncovering the core ideas, the things I used to have on my list that I needed to teach them, they are now actually teaching themselves with my guidance through a very specially designed lesson plan, unit plan, year-long plan. Before we begin, I want to shout out that this is the end of my Electrons sequence. The unit pertaining to the NGSS standard that reads, students will use the periodic table as a model to predict the relative properties of elements based on patterns of electrons in their outermost energy level of atoms. Phew, there's a lot tied up in there, isn't there? Patterns of electrons, outermost energy levels come from students being able to know and work models, multiple models, atomic models and theories devised by scientists in history, properties of elements, tying in observational physical properties, but also the purpose for studying this entirely, which is chemical change and chemical properties. And then really the crux of it is getting the periodic table hacks that allow us to know it all super fast. They may as well just call this whole unit the periodic law. But in doing that, it would negate maybe the importance of the behavior of those electrons and the chemical properties and that whole piece. Because when we do just focus on the periodic law as a lesson, as an idea, especially in a lecture format, we are missing the opportunity to connect and give it the critical emphasis that it really deserves and requires. As per science and engineering practices is laid out in the NGSS or whatever state adaptation you're using, this lesson goes directly to using the periodic table as a model. Perhaps you could also extend it to the electron configurations as a model. But really the whole thing students are doing here is obtaining, evaluating, communicating information. But the obtaining information part is coming from their brains and the periodic table. But it's really an art of knowing, pulling in already what they've known. This lesson can almost be used as a review for the whole unit, the first half of it anyway. And then of course, we're tying in that piece where we argue from evidence. That's the inquiry-based piece. That's the discovery piece. That's the part you might need to guide a little bit. But as a periodic law lesson goes, cross-cutting concepts, we're not dealing much past the pattern because the periodic law is the pattern that's on the periodic table. That's what we need students to get to, and then that's what we need students to use. So While structure and function also plays a part here, and I try to impart a big aspect of that, big emphasis on that in my classroom with my students, that what we can glean from the periodic table leads to bonding, leads to chemical change. That is also true for the entire unit. So not so much there, but a little bit of a sprinkle in. I hope you've watched some other video of mine before this one. And if you have, you know that I have a 5-part framework for lesson planning. And this one does not disappoint. This one does not diverge from that framework. If you have not seen any of those, I'm going to go through them real quickly, but I also will point them out in my lesson. The first part of every one of my lessons, inquiry-based chemistry lessons, is a review and preview, which is intended as a warm-up, as a bell ringer, but not a simple one. One that always requires students to activate knowledge they've gained, academically acquired, or life experience that you can tie in and connect to the content you're teaching that day. Then we move on to some lesson objectives presented as intentions and success criteria, where the learning intentions give the what and why of the lesson, and the success criteria ensure that your students know how to engage and how to be academically achieve with the content and the experience you've given them. So literally, they could use them as a checklist, and so could you. There's always an activity. Always, we can call it an inquiry-based science activity, but it's a discovery-based activity. It's one with task instructions that are usually more general, but are accompanied with an artifact outline that is very specific and designed to enhance whatever cross-cutting concept we're going after truly. Today, it's patterns, and you're going to see that in the outline of the data that students will collect. That is the point at which they are obtaining and evaluating that and communicating truly by marking it all down to keep it in a place, just like a science notebook. They are doing that very central piece of science. And then there is, this is like part 4 of the framework, would be a data-dependent analysis. That's what I've called it forever. I don't know what you would like to call it. It's basically the same thing. It's where we make the inferences. It's where we take what we knew before, plus what we have just seen in an observation-based inquiry activity, and connect them to come up with some new knowledge, to create new knowledge every day. Imagine that. Imagine that, working at the top tier of a taxonomy every day. Critical thinking through the roof. That's what we're going after. Finishing up the lesson with some skill practice, tasks students will see on standardized type assignments, not detailed written scenario-based situations, but that practice that can become more, they always get better with rote repetition, okay, and progress, because then you can connect them to another resource where they could do that repetitive practice on their own. But they've tried it with you, they know the basics of it, and then they can move along with that. So let's dive in. My periodic law lesson begins with the review and preview, in which students will collect all this information. So I give them a periodic table, and I assign them 3 elements from each of 4 groups. Group 1, 2, 1 and 2A, and also 7 and 8A. Okay, because the periodic law is completely focused on group properties, elements within a group having similar properties. So what we're going for first is the microscopic properties, the atomic properties, the model-based properties that students have learned to pull from the periodic table and its very unique organization, it as a model. Now what you're looking at here is the answer key. And there have been times that I've presented this lesson in a way that I didn't have a whole lot of time left to have them extract it all and do that thorough, deep digging review. So I just gave them this. And then I said, let's look at this, figure out the 4 things that are similar among all the atoms in a specific group. So you can approach it that way, but what I really love to do and where this really comes alive is if you separate it into each group. Maybe and it's a great unique opportunity for your students to collaborate too. So tons of flexibility here for that. You can assign each student an element and put them in groups of 3. And that would give you 4 groups of 3 where you can have, more than 4 groups and just assign more than one group gets group 1 and more than one student group has assigned group 2 and so on. Or you could have small groups of 4 students and each student complete all the information for 3 elements. Now that's fantastic practice. That is really, truly review and preview. Or you could have every student do everything, but that takes so long. So when you're thinking about delivering inquiry-based chemistry lessons, inquiry-based science activities, active learning in your classroom, going student-centered, time is a serious component, and divide and conquer is a very real, doable delivery method. Also, students like to have help. Also, as this is the end lesson in a unit sequence, what students don't know, they should be able to get help from other students. All right, I digress. I get so excited. What we're looking at, what students want to be able to do in this review preview, and to be clear again, they would have to be able to do for this to be successful. The first portion of this lesson anyway, is familiarity with group and period numbers on the table. Which one's a group, which one's a period, identifying their location. Then citing the number of valence electrons, which they can get from the group A number. Determining the valence electron configuration, which they can get from our block regions of the diagram, SPDF. Those, of course, separate lessons that I've delivered. Gain or losing electron. How does an atom achieve its octet, achieve stability through the octet rule? Will it gain electrons or lose electrons? How many will it gain or lose, if it will? Now, time out. I know not all atoms gain or lose electrons. Some share. Isn't this misleading? I haven't found it to be a real problem. Because when I'm done with this, I'm going to launch into chemical bonding, and I'm going to start with ionic bonding. And I have laid all the foundation for going there. When it comes time to do covalent, I merely need to say, guess what? I left out a detail. We don't just give and take electrons. We can share, and sharing is caring. And it's effortless. No problem. They accept that just fine. In stride. I promise you. What's the charge once ionized? And I see these components, especially, teaching the octet rule as if gain and loss, slipping it in here into the periodic law. It's part of it. It's part of the periodic law. It is. So it's perfectly suitable to reinforce this concept as well. Students get excellent practice with this. What they don't know, you can help them with. What they don't know, their friends can help them with. And then they come out being able to say what? The number of valence electrons in every group is the same. The valence electron configuration is nearly the same in that our group 1 elements all have 1 electron in the s orbital. Our group 2 electrons have 2 electrons in the s orbital. Our group 7 electrons have 5 electrons in the p orbital, but in the whole valence, it's S2P5. And same our noble gases, right? And honestly, at this time, having already taught the octet rule, students are already familiar with the fact that group A, 8A atoms, they are royalty, they are celebrity, they are nobility, every element wants to be like them. And they share 8 valence electrons in common. So that's actually already a piece that they already have an octet that none of them get charged. If they know that, they can work backwards through 2. So pretty much every property I'm asking them to conjure up through a periodic table hack, a periodic table trend, a periodic table pattern is something that they have in common within a group. And then just including that group and period piece for each element so that you can remind students where it comes from, that the group number informs number of valence electrons, that the period number informs the distance from the nucleus and that valence shell orbital, and is the same whether we're looking at a Bohr model or the Schrodinger electron configuration orbital diagram kind of model. And this is the beginning of the periodic law. All elements, atoms of the same group, have these things in common. You know, I typically would present a review and preview and then give learning objectives for the whole lesson. But prior to giving this particular review and preview, I will set this up for students and let them know, today I'm learning about the periodic law. For all the same reasons we did every other lesson in this unit, to use the periodic table instead of detailed models to get to those chemical properties, to get to the potential and prediction for bonding. That hasn't changed. But the reason I might set this apart as learning objectives for this part of the lesson and to start them out this way is just in case it takes you the whole period. This year with my students, it took me the entire period to deliver the review and preview, which is no longer a review and preview, it's the lesson, right? And just letting them know this is what you're going to do. You're going to use the periodic table to list 4 what I call microscopic, because I like the notion and the alliteration of chemistry being micro to macro. Also, that's the name of my year-long chemistry curriculum. If you're interested in checking it out, get 5 free lessons representative of what's in there. It's in the link in the description below. But listing them located in the same group in the periodic table and then explaining the properties that are similar. That's the first goal. So it's totally appropriate for students for you to separate this out, have students do this thing. And if it doesn't take them a long time and you can accomplish the next part of the lesson, go for it. If not, you can have kind of a clean break there, right? Now, I'm actually going to share with you I have in my notes here, some outcomes of students. I mean, they do this. I don't include this a lot in my videos, but it's real. They do it. This is proof. Asking students, what do atoms of elements located in the same group have in common? And they can write about it. They can express it. I promise you it works. Second portion of this lesson is looking at the macroscopic piece. Okay, so at the very beginning of the school year, if you would teach chemistry, you probably do this too. At the very beginning of the school year, when we frame out for students the why and the what of chemistry, we want to be able to learn about what we can't see because it creates what we can see. So this lesson just reinforces that in a super big way. We can now say, you know, all those atomic properties you just listed, all the number of valence electrons and where they live and how they satisfy octets and how we can predict they will bond, we're going to see that. We're going to see the similarity in how it presents in real life, macroscopically, what we can see. And I've got some videos to share for that. So there's some video evidence to identify physical, not just chemical, but also physical property similarities among atoms in groups 1A and 7A. So that's part of the reason I chose this layout of elements. You know, if you're watching this, you're probably a science teacher or a scientist. We would like to, if possible, always have triplicate evidence, but there's not enough room on the screen in this case. So we'll go with duplicate evidence. I chose group 1 and 2 for metals to represent metals, group 7 and 8 to represent non-metals, of course, that group 8 being super important as to the noble gas feature. But the video evidence I have that I can find is in group 1A and 7A. So it's complementary in that way. Throughout this unit, I have been saying, hey, sometimes you'll see a word wall in my lessons, and most of the time I don't give a definition. But a lot of the lessons in this sequence I have. And that's because students needed to have that perspective, that context in order to go into their activity. Here they don't. Here the main term they need to be able to define and use accurately is the periodic law. It's also a concept. And it's the one that they're unearthing in doing this activity. It's the one that by this time if you deliver the review and preview the way I did, you've already accomplished half of it. You've got the why of what they see being similar. So this is something you'll revisit at the end of class as, hooray, light bulbs went off. The room is totally lit up because now we know what the periodic law is. But this is our activity. And if you've watched many of my videos, you know that my task instructions are pretty basic, pretty simplistic, pretty general, because I do provide students with an artifact outline that is plenty detailed and structured graphically, spatially, and scaffolded to lead students through the process of basic observation and asking questions through more specific evidence citing and inference. So here you see students just watch a video about group 1, watch a video about group 7, and in total we're talking about 6 or 7 minutes of video. Likely if you have them doing it independently or in small groups, they're going to pause along the way. So time in total for this activity, I'm saying probably like 15 minutes, because the artifact outline I give them is pretty detailed. And they do tend, I've had groups of students who are super descriptive, and you know, the more specific we could be in our observations, the more evidence we have to cite, the more insightful and thoughtful we could be about in our inferences. So I definitely don't discourage that. I never, ever rush students when it comes to observations, because they're the launch pad and the key pin to everything that they're going to do in my class. So the more time I can give them for that, the better. Firstly, I asked them to list the elements in the video itself. In the alkali metal videos, I'm pretty sure it starts from lithium and goes through cesium. So there's 5 different elements. I mean, and this is important because hydrogen is included in group 1. But hydrogen's a gas. It looks nothing like the other elements, and it's not included. And also when they watch the video and you see what cesium does in water, you would understand why somebody's not throwing francium in there. So there's a little bit of conversation you can have about that as well. It's important for them to list and see what was in the video. Whereas in the halogens, they're exploring fluorine, chlorine, bromine, and iodine, and nothing below that. And those are certainly our most common. Prompting them to list the similarities and differences in the same group and in the same period. So with your higher achieving, quicker learning students, you may just be able to say, what are the similarities and differences? And maybe they will be so descriptive that they will include all of the most notable parts. And in the alkali metal video, there's not much to say besides what's the state of matter. They're all solids. What's the color and appearance? They're all some shade of gray and shiny and soft. You can cut them with a knife. How do they behave on exposure to air? They tarnish. What's their behavior with water? Actually, we should be looking at the answer key, huh? They react pretty violently. They let off lots of energy, various levels of energy, and there's some differences there as well. They're all solids, no differences there. They pretty much all look almost exactly the same. But when it comes to chemical properties, some react more quickly than others in tarnishing. And with the water, some are like super violent. And the narrator actually does give that perspective. The narrator does basically say, here's the chemical equation for the process. This is the same for all the metals. It's just so much more energy is coming off from those elements located at the bottom of the period. In the halogens video, it's a little different because we can make a nod to the state of matter, which spans all the states of matter. We have fluorine and chlorine, which are gases. Bromine's a liquid and iodine's a solid, but students can see them all as vapors because of the way bromine and iodine behave at room temperature. So they're all volatile, but they are all different states of matter also. As color and appearance goes, they're all gases that have to be contained in order for us to see them, but also they're brightly colored, unlike our group 1A elements. Even though they're different colors, we can contrast that with the group 1A because they do have color. They're like rainbow colors. They react with metals, okay? So you're not reacting your metals with your metals in the group 1A video. But that's because it's very hard to point out any lack of reaction with our halogens in air. anytime you present air to students, they take it for granted. It's like, it's a void. It's not really air, right? So that's not included, but the behavior with metal is, and it has the same sort of feature as it does with the group 1A metals with water, in that the reaction itself is the same, but it's more violent or needs a push depending on which one it is. And then similar though to our group 1 is the behavior with water. There are also other demonstrations in this video about halogens, and so if students were to try to write everything, they'd be like writing the transcript of the video. By providing this very specific outline for them, and to not just say what are the similarities, but yes, there are some differences too, be mindful to separate those in your mind. It gives them a really deliberate way of looking at this, a really deliberate perspective. And this is going to be where most of their time is. Then we prompt them to say, hey, what's the same between group 1A and group 7A? And if you deliver this lesson and you see the time is ticking, you might let them finish up their observations, talk about those briefly, and then pose this question. Maybe they don't get to answer it on their own. You're going to maybe get crickets. Because they're like, really? Did she just walk me into this situation where there's that nobody wants to say there's nothing similar, but that's the golden ticket here. Group 1, group 7 are on opposite sides of the periodic table. We're talking metals and nonmetals. They're in different periods. I mean, same periods, sorry. Sodium and chlorine, for example. Lithium and fluorine, for example. Potassium and bromine, for example. Same periods, different groups. Nothing in common. Nothing. Sometimes my students will scrape for a similarity. And, they're scraping. There's nothing. And that's the whole goal. But meanwhile, you're practicing these science skills of obtaining and collecting and evaluating evidence, citing evidence, arguing evidence. In the bottom corner here, this represents some of those assessment-based success criteria that your students need to be able to do. Look at the periodic table. See what would you expect based on this? How can you translate what you've learned in this experience to the periodic table? And again, if you have ample time, you have quick. There was a time I could get through all of this, every lesson, every day, one per day, no problem. And maybe it's with experience, or maybe my students are shifting. I hear a lot of teachers blame COVID for all the things that are different about our students, and maybe that's real. But I have to work much more slowly than I used to. This year, for example, we did not do this. Students did not have any time to work on this themselves. We did it as a group at the end, part of skill practice, because it is skill practice. But one thing you would want to definitely point out after you have collectively reviewed and talked about this is that the micro and the macro, they go together. All of that students have learned about the electrons, about the electronics of an atom, presents itself in physical and chemical properties. And so does halogens. And if their microscopic is wildly different, it is lose one, gain one, plus one, minus one. So are their physical presentations and chemical properties. So again, we can summarize this at the end. Much like we did throughout the entire unit of lessons, metal versus non-metal, here we're going back to groups and periods. Elements in the same group have similar properties. Elements in different periods, in the same period, have different properties. And it's here that you're clearly defining the whole entirety of the periodic law, and then you can share that with your students. Guide them through that skill practice, which says, let's compare these two. And what I like to do, I do work in an online school, cyber school, right? So I can highlight on a board and everybody's watching me, but I'm sure you and your fancy smart boards, you can do that too. I would highlight sodium and chlorine and say, same or different. And we might go through these one by one. Actually, the one I start with is potassium and arsenic. because students know potassium's in bananas. And they've been through biology by the time they get to me in chemistry, and they go, oh, you need potassium to live. But arsenic, that I'll say, but arsenic. What do you know about arsenic? Arsenic's poison. Potassium is not poison, arsenic is poison. And at the very beginning of the year, in one of my intro to chemistry lessons, we're talking about chemical and physical properties. And one chemical property they note is toxicity. So right there, I'm able to say, hey, remember this? Toxicity is a chemical property. It's a reaction that's happening in a biological system. Arsenic does it, potassium doesn't. Different. And they're in the same period. So if they can always go back to that comparison, they will always see that elements in the same period are wildly different in their properties, but those in the same group are not. And then we could go through a series of practice like silicon, which one is similar, selenium, which one is similar, and so on. There's even a little excerpt here I pulled from the internet, not my original work, so I have blurred it out, but you certainly will get it as part of my TPT lesson if you were to purchase this from my store. Also, throwing out there, like I say, I always like to include adaptive practice for your early finishers, or at least even at the end of class to say, hey, please follow up here to get more practice. And there's also exit tickets that I include because that's a best practice. I never have time for it, but if you do, go for it. I feel like there's so much formative assessment going on during my entire class period. I don't really need exit tickets that much, but I'm going to throw them in there every once in a while. They are powered by Book Widgets, and Book Widgets is a fantastic, albeit alternative and different tool for transforming your lessons into something that is uber student-centered, something you can share with your students as just a web link that they can complete and download and save and print for their own notebook, have your entire lesson right before them. Programming it so that it'll show you immediate feedback as to correct or incorrect. So students can complete this lesson confidently even without you present. And if they keep clicking answers that are incorrect, they know they should just maybe stop and get with you first. Or maybe they go through the whole thing and they're getting positive reinforcement through the whole thing and they go, wow, I don't even need to ask Mrs. Gross's a single question about this. I am ready for this part of the test. In all of the lessons I sell in my Teacher Pay Teacher store, the digital notebook is included by popular demand. If you're a chemistry teacher, I hope you've seen throughout this lesson just how complementary this lesson is to all the others in the sequence and all those things students would have had to do, and how key it is to this scope and sequence for me to put the periodic law at the end of a lesson. And I hope this inspires you, or if you are some others teaching some other secondary science, that it inspires you to do the same, to look at the status quo, consider how you might juggle things up to ensure discovery and inquiry, not just within one lesson, but in a larger story that you're telling your students.